All right, now we can discuss energy. First, we start with the idea of work. So we have work equals F dot D, where D is the distance that the force is applied through, which is F D cosine of theta. Now we can just write it as F D cosine of theta from now on for convenience, but generally you have to start with F dot D to get there. Now we can start to discuss energy. We start with the idea of work, which is work equals F D cosine of theta. Now when we apply a force to a mass, over a distance d, the force does a certain amount of work. So what does it do? Well, it's Fd, basically in this case, work would just equal Fd. So we know that a constant force applied to a mass is going to accelerate the mass. So we can describe that acceleration as F over m. And we can consider how fast it's going to end up, or how much speed it's going to gain. So suppose it's starting with some velocity v0, and it ends up over here, there's the mass, with some velocity, final velocity v. What's the final velocity? Well, we could use the equation v squared equals v0 squared plus 2a delta x. So in our case, delta x is d, and acceleration is F over m. So v squared equals v0 squared plus 2 F over m d. And if I multiply by m divided by 2, we get 1/2 mv squared equals 1/2 mv0 squared plus fd. And if I put fd on its own, I'm going to get fd equals 1/2 mv squared minus 1/2 mv0 squared. So notice that fd is the work. So this is the work. And what's all this? So this right side is clearly a difference in quantities that all look the same. Like this is the quantity at the initial time, and this is whatever quantity that is at the final time. So it's helpful at this point to make a definition. So what we do is we define 1/2 mv squared as the kinetic energy. So kinetic energy is 1/2 mv squared. That is, that's the energy of movement. And then this is the kinetic energy initial, and this is the kinetic energy final. So what we get is work equals delta Ke. And this is the work energy theorem. So what it says is that work changes the kinetic energy. So if you think about it, positive work is going to give you a positive delta Ke, which means it's going to try to speed things up. And negative work is going to give you a negative delta Ke, which means it's going to try to slow things down. So kinetic energy is an energy in the units of joules associated with the mass of the object and the velocity of the object. So here are our equations. To clarify, the top one is a definition of work. Work is Fd cosine of theta. The bottom one is not a definition of work, but rather a relationship between work and energy. That is, it's the work-energy theorem. So the top one is the definition of work, but the bottom one tells you what work does, which is that work changes kinetic energy. So we have an example here. A force of 200 newtons is applied over 3 meters. Find the change in kinetic energy and the final velocity. All right, so let's first draw our force here. So that's 20 newtons. And we have a distance of 3 meters that the object moves. So find the change in kinetic energy. So using the ideas of work, we can find that directly. I mean, we could actually figure out the acceleration from this. We have force and mass, so therefore we get the acceleration. Then we could calculate the final velocity, which would give us this thing first. And then from the final velocity, we could use the definition of kinetic energy and find the change in kinetic energy. Okay, of course. But instead, let's use what we know about work and the work-energy theorem. So work equals change in kinetic energy. So that's going to get us the answer directly. All right, So what is work? Force times distance, in this case state equals 0, so it's just Fd equals change in kinetic energy. So change in kinetic energy equals 20 times 3, which is 60 joules. Okay, so that's the answer to the first part. Then, assuming it starts from rest, I didn't say that, but if it starts from rest, we can find the final velocity. So from Ke equals 1/2 mv squared, so Ke is 60, 1/2 m is 5, and you get V is 4.90 meters per second. Okay, see, we know that if we apply a force on a mass over a distance of d meters, then the work done by the force is F times d. Okay, so let's take this situation and make it vertical. That is, we have an object at a certain height h above the ground, and it falls. So it starts out at h and it falls to the ground. So let's draw in our force to see what's going on. The force is the force of gravity. And when we describe the object's motion from the top to the bottom, we can refer to the work done by the force of gravity. So that is, the work done by gravity is work equals force times the displacement. Okay, so, and let's put in the angle here so we can sort of be clear about that. Okay, so the force is what? mg. And what is the displacement? So I drew the h here as just like a distance here. But really when we go from the top to the bottom, there's a displacement, which is a vector. So h is this vector going down, and it has a magnitude h and a direction going downwards. So h will be our displacement, the magnitude of it. So what about the angle? The angle is in between the force and the displacement. They're both running downward. So the angle between them is 0. So really, so this doesn't exist. So in other words, cosine of 0 is 1, so it's just mgh is the work. So the work done by gravity is mgh. So as the object falls, the work done by gravity is mgh. And what happens if it's not falling? Suppose we have a shelf with some height h. Okay, what's going on here? All right, so if it were to fall, it would do this much work, but it's not falling. But we know, we have sort of an intuitive idea that if a heavy object is on a shelf, that it has some sort of energy to it. You know, you would not be comfortable maybe like sleeping under the shelf if this object, this heavy object were on the shelf. If the shelf breaks, then what happens? Okay, if the shelf breaks, then the object falls. Okay, so if the shelf breaks, then gravity can do mgh worth of work on it. So we can consider that when it's up here, it has some sort of energy that it's getting ready to do. That is, there's energy of a potential nature. So we call that potential energy. So potential energy is equal to the work that gravity would do. So work that gravity would do. So for an object at a certain height h, then we'd say the potential energy is mgh. So that becomes another formula to know. But if you think about it, what does it really mean? The potential energy is the amount of work that gravity would do. So if we say the potential energy is mgh, that means an object at height h has a certain amount of energy, which means that gravity would do mgh worth of work if the object fell. All right, when we have a mass up here at height h, it has potential energy equal to mgh. And what about down here? Down here, h is 0, the height is 0, so the potential energy equals 0. So notice that when this object fell, it lost potential energy. And how much potential energy did it lose? It lost mgh worth. So that's the amount of work done by gravity. Work done by gravity is mgh. So gravity did this much work, and that caused us to lose that much potential energy. In general, we can say that work equals negative change in potential energy. So just as work increases kinetic energy, work decreases potential energy. All right, so when the object is here, we say that it has potential energy equal mgh. It has that much amount of energy built up. That means that's the energy that could turn into motion, or it's the amount of work that gravity would do. Okay, when it does fall, so now it's like free to go. And from here to here, so it's actually falling down, gravity does work, which is mgh. Now let me specify h here. All right, when it gets to the bottom, just before it hits the ground, it's going to have a certain amount of kinetic energy because it's moving, and it's moving very fast. So how much is that equal to? Well, from the work energy theorem, work changes kinetic energy. So when it goes from the top to the bottom, it's going to change the kinetic energy by this amount. So we say that it has some sort of kinetic energy at the bottom here, which is equal to 1/2 mv squared. And the amount of kinetic energy that it has at the bottom is equal to the amount of potential energy that it had at the top. So what happens is when something falls, the energy changes from potential, that is like energy that could be used for something, to kinetic, which is energy of motion. And that's carried out by the work that gravity does. So gravity does work on the object, and we have potential energy getting transferred into kinetic energy. Now this gets us into the idea of conservation of energy. Okay, conservation of energy kind of makes you think of like saving energy, but that's not what it means here. Conservation means that something stays the same. There's a whole class of laws in physics called conservation laws, and these are laws which state that some quantity, whatever it is, stays the same throughout some interaction. So in this case, it's energy. We have conservation of energy. Next up, we'll have conservation of momentum. And there are also other conservation laws, conservation of electric charge, for example. So there are certain quantities that stay the same, and knowing that helps us solve physics problems. So in this case, we have conservation of energy. The potential energy at the top is equal to the kinetic energy at the bottom. When we use the law of conservation of energy, we don't have to know exactly what happens from the top to the bottom. Of course, here it's quite simple. But we could get a more complicated case where all we know is the initial state and the final state, and that's all that matters. Because we could say that the initial energy equals the final energy, and that's all we need. So conservation of energy means that initial energy equals final energy. Or you could write it as delta E equals 0, where E is the total energy. So E equals potential energy plus kinetic energy. And if you have other types of potential energy, those would be included in here too. And also if you have something like energy being converted into heat, mechanical energy being converted into heat, such as with friction, if you take into account all the energy of the system from the beginning to the end, then you should be able to add it all up and it equals 0. So practically sometimes we can't account for all the energy because friction creating heat is a very complicated phenomenon, and it's hard to measure the heat energy produced by friction. But theoretically, all the energy should be accountable. Energy is not created or destroyed. If you happen to know that E equals mc squared, that's Einstein's famous equation, what that means is that mass can be converted into energy and energy can be converted into mass, so then energy can be created or destroyed. But basically what we say is that the mass has some sort of energy associated with it. So again, if you account for all the mass being converted into energy and energy being converted to mass, you should end up with a total accounting of energy that where no energy is ultimately created or lost. Just as we can have potential energy converted into kinetic energy, we can have mass converted into some sort of energy. So as long as you account for it all, it should all be there. All right, so we have an example here. 5 kilogram mass falls through 12 meters. So we want to find the work done by gravity and the change in potential energy. So the work done by gravity is, as we've said before, it's the force mg times the displacement, which is 12. So we know that the work is equal to mgh, but I don't want to start with that equation because that's not a fundamental physics equation. That's this equation applied to the case of a falling object. But what we want to do is start with that equation and then apply it. Okay, so we get work equals Fd cosine of theta. F is 5 times 9.8. The displacement is 12. And the theta is 0 between the displacement and the force. So it's just cosine of 0 is 1. But we can write it in anyway. And we get 588 joules. All right, now the change in potential energy. So you could calculate the potential energy here is mgh, which is going to be 588, and then down here the potential energy is 0, so the difference between those two is negative 588. Or that we can use this equation here. Work is equal to the negative change in potential energy. So B, that would get us work equals negative change in potential energy. So change in potential energy equals negative work, which is negative 588 joules. So for these answers, sometimes you can intuitively just kind of figure out the answer, but you have to be able to explain it somehow. You have to be able to explain that the reason this is negative 588 joules is because we're starting with this equation. Work equals negative change in potential energy. We have the work done, so the change in potential energy is negative that, so negative 588. Or, like I said, you could have said potential energy up here is 588, potential energy down here is 0, so the change in potential energy is 0 minus 588, which is negative 588. All right, now the object is pushed back up. So there's going to be some external force pushing it back up. Maybe your hand or some crane, some pushing force which is pushing back up. Okay, so find the work done by the pushing force. Now we don't know what the pushing force is, and whether it's constant, we don't know what its nature is. But let's make one assumption. There's an easier way to do this, but let's look at the pushing force and make an assumption that once you get this thing moving, you could have it be moving at a constant speed if your pushing force is just balancing out the gravity. That is, you first have to get it moving, but once you get it moving, then you're basically just doing mg worth of force until it gets all the way back up. So that's one way to bring it up to the top. So in that case then, if F equals mg, not going down but really going back up, we're balancing the force of gravity. And like I say, first you got to get it moving. But once you get it moving, you can just keep on doing F equals mg, and the net force will be 0, but once it's moving, it'll keep on going up. Okay, then the work done by the pushing force is work equals Fd cosine of theta. So it's mg and times the displacement h. Now, here your displacement is h in the positive direction. If your displacement is up and your force is up, then your angle is going to be 0. So let's put in some numbers. mg, which is 5 times 9.8. So that's going to be 5 times 9.8 times 12 cosine of 0. Because like I say, if your pushing force now is in the direction of your displacement. This is like a separate problem from that. We're pushing an object back up. So the displacement now is positive. So that's going to get you positive 588 joules. Okay, so that's assuming that we're pushing with this constant force all the way up. But what if we're not? And in fact, in reality, you're not, because you have to get it moving. So you have to like push with more than mg to get it moving. But you could push it really hard for most of the way and then really lightly for the last little bit. So the force doesn't have to be constant. So there's an easier way to figure out what is the work done by the pushing force. The other way to do it is to say that the work done by the pushing force is opposite the work done by gravity. It's opposing gravity. So whereas gravity is pointing down, our pushing force is pointing up. So as we lift this up, what's gravity going to do? Well, gravity is trying to pull it down, and you can end up with a negative value, as we'll see. And the work done by the pushing force is positive, because we're moving it in the direction that we want it to go. So let's do B first and then figure out A. So B is the work done by gravity. Work equals force times displacement times cosine of the angle. So that's going to be mg. So 5 times 9.8. The displacement is 12. Now, we've got to be careful here. Gravity is going down, so let's make our mg here. The mg I had going up was when we assumed that the pushing force would be balancing gravity. So let me sort of take that assumption away. So we have some pushing force going up, but we have gravity going down in mg. All right, so gravity's pointing down, our displacement is up, so what's the angle between them? Okay, well it's not 0 because we have gravity going down, displacement going up, they're going in opposite directions. So that's cosine of 180. Cosine of 180 is negative 1. So you're going to get a negative value here. So negative 588 joules. So the work done by gravity as we push it back up is negative. That's because we're going against what gravity wants it to do. Gravity wants you to go down, but the displacement is up. So overall, are we doing negative work? Well, no, because we have a pushing force. So we're balancing what gravity's doing. So the work done by pushing force should be opposite that. So, gravity wants it to go down, the pushing force wants it to go up, and it's going to be exactly the opposite amount. So, work equals positive 588 joules. So now we can do A. So looking at part C, the change in potential energy, we can use the idea that work equals negative change in potential energy. That is, work equals negative change in potential energy. So that means that change in potential energy equals negative work done by gravity. So we have to be very careful. This is gravitational potential energy. We could put a subscript G on there. The change in potential energy is related to the work done by gravity. So it's equal to negative work done by gravity. So negative 588 is positive 588 joules. You don't have to write the positive, but I'm putting it there just to emphasize it's opposite the work done by gravity. And that makes sense because we're going from potential energy is 0 to potential energy is 588. All right, here are some examples to do. We have a 7.9 kilogram mass pushed with a constant force of 12.6 newtons over a distance of 2.4 meters. So using energy concepts, find the final kinetic energy, that is when it gets to this point after 2.4 meters, and find the final velocity. So what we get is 30.2 joules for the final kinetic energy and 2.77 meters per second for the final velocity. So you could do it using kinematics, but that's not the point here. The point is to use the energy concepts and to correctly use the formulas so that you can go step by step, starting with the formula and then going step by step to get the answer. All right, here we have a 78 kilogram mass following a distance of 12 meters. So we want to find the work done by gravity and the change in potential energy. The work done by gravity, we get 9173 joules. The change in potential energy is negative 9173. So make sure those you can do starting with a formula. So you don't just want to calculate MGH and negative MGH. You have to be able to start with a formula and justify the answer. And in doing so, you'll explain very clearly why this is positive and why this is negative. The equations will show that. So again, you don't just want to calculate to get the answer. You want to start from an equation and get the answer with the correct sign. All right, so then now part 2 is the object is pushed all the way back up to the top. So what is the work done by the pushing force? So that's a positive 9173 joules. So the work done by gravity and the change in potential energy. So for those two, you would need to start with an equation and work through and show that you can get the correct sign. You don't want to get the wrong sign and then just sort of put a negative sign or cross out a negative sign at the end because you know it should be negative or positive. You want to be able to work through with the correct angle and everything so that it comes out with the right sign. All right, here we have an 18 kilogram mass that drops through 1.5 meters to get to the ground. We want to find the initial potential energy, the final kinetic energy, and the final velocity. All right, initial potential energy. So first we're going to start with an equation, and that is potential energy equals mgh. Okay, so that's 18 times 9.8 times 1.5, which is 265 joules. So again, you don't want to just start with the calculation, you have to start with an equation and then go step by step from there. The physics is here, so that's important. And then the rest of it is like algebra and calculations. Okay, the final kinetic energy. So what's going to happen when it gets to the bottom? What's the final kinetic energy? Well, you know it's going to be 265 joules because whatever potential energy it started with, that's what the final kinetic energy is going to be. So how do we actually come up with that result? You don't want to just write the answer. Okay, one thing not to do. Don't write PE equals KE. There is no law of physics that says PE equals KE. That's not a fundamental law of physics. That is an application of conservation of energy for specific cases. But we don't want to start with that. What we want to start with is EI equals EF. That is the law of conservation of energy. If you start with PE equals KE, you're missing a step. You're missing the physics. The physics is that there's a law of conservation of energy, and we have to state it. So we state the law of conservation of energy, then we apply it. The fact is, there are cases where PE is not equal to KE. That is, if this had an initial speed, you'd have PE and KE up here, and then just KE at the bottom. We'll do some examples like that. But for now, we happen to be doing a case where the only energy up here is PE, and the only energy down here is KE, and they're equal to each other through conservation of energy. So, again, you have to start with conservation of energy. Then move on to the specifics. Okay, the initial energy is what? The initial energy is PE up here. So then we can say PE equals, and what's the final energy? The final energy is kinetic energy. Alright, so we get KE equals PE, which is the initial potential energy was 265 joules. Alright, so that justifies it. We can't just say it's 265 because I know. We can't say K equals PE, so therefore it's 265, because that's not a general enough equation of physics. That's an application of an equation of physics. So we need to go all the way back to the source. This is the law of physics that says we can do all this. This is the law of physics that says we know the answer is going to be 265. So you start with EI equals EF, and then that gets you PE equals KE, and so then the KE is going to be equal to the PE that we calculated up here, which is 265. All right, final velocity. KE equals 1/2 mv squared. So I'll let you calculate it, but the answer is 5.42 meters per second. Okay, now on to this one. A 25 kilogram mass gains 80 joules as it falls. What was its initial height? Okay, what does it mean gains 80 joules? What type of energy does it gain as it falls? It gains kinetic energy. So that's going to be a change in kinetic energy. So initial height, how can we find initial height? Well, height shows up in the potential energy. So we can start with the idea of conservation of energy. We can say E initial equals E final. Okay, what's the E initial? At the top, so we can actually kind of write it up here, mass. Okay, at the top, E initial is what? Just potential energy. And at the bottom, E final is kinetic energy. Okay, that's in this case. It's not always the case that it's so simple. Sometimes there can be other sources of energy that we have to consider. But for now, in this problem, the initial energy is the potential energy that it started with, and the final energy is the kinetic energy that it gained, that it ended up with. All right, so EI is PE, and EF happens to be KE. And once again, don't start with this equation because that's not a law of physics. This is the law of physics. EI equals EF is the law of physics. We're applying it here, and we get this. So now we get mgh equals KE. So the amount of energy, that's the amount of energy that it gained. If it started from 0 KE, then it gained 80. So it has 80 joules of kinetic energy at the bottom. All right, then plugging in for mass, so 25 times 9.8 times h equals 80. So that gets you, h is 0.326 meters. Here are two more examples for you to do. We have an 8 kilogram mass that falls 3.5 meters to the ground. We want to find the initial potential energy, the final kinetic energy, and the final velocity. So the initial potential energy comes out to 274 joules, the final kinetic energy comes out to 274 joules, and the final velocity is 8.28 meters per second. So in any of these examples, you can't just do the calculation and get the answer. You have to be able to explain for example, like the final kinetic energy, you'd have to go through, as we did, the idea of conservation of energy to be able to come up with the answer. All right, and then finally, a 15 kilogram mass gains 600 joules as it falls. What was its initial height? So again, the calculation is easy, so you don't just want to do the calculation to get the answer. You want to start with conservation of energy, if that's what you're using, and then go from there. And the result here is 4.08 meters.